and welcome to AD.ACADEMY. In this video, we are going to solve this physical system modeling of these two masses M1 and M2 connected with these two springs named as Ks and Kt. We're also going to draw a block diagram for this very simple mechanical system. It's a little bit more complex than the videos that we have covered before, but the method is going to be exactly the same to draw the block diagram. For the block diagram, we have to first go for the free body diagram and then drive the equations for the total net force applying on M1 and M2, and then according to those equations we are going to draw our block diagram. So in order to draw the free body diagram, we are going to take this mass block exactly the same way, that's showing Fi as an input force, Xt as displacement happening across M2, and the only thing that we have to understand is when we'll apply this input force Fi in downward direction, the force or the reactive force produced at Kt here will pull this mass upward. So we are going to have a second force on this M2 which will pull this mass upward, and that's happening across this Kt, so we'll give this force name Fkt. Now for the second block diagram, we are going to use exactly the same thing, but we'll change this mass name as M1. So let's draw this mass M1 here, and we have this M1 here, and now the only thing that we have to pay attention here is again the force. Now here when we'll put this Fi as the input force, the reactive force produced by Kt was pulling this mass upward. However, for M2, because of this input force Fi, this mass M2 will pull this mass M1 downward as well, which means Fkt, which was here as a reactive force, will turn as an input force for M1 and pull this mass downward, and as the reaction, the force produced by Ks will pull this mass upward. So we are going to have this another force which is named as Fks will pull this mass upward. So now we can draw this the direction of force Fkt, and this will pull this mass upward. We'll call Fks, and we'll have this displacement in the same way is called Xs. Now we got our block diagrams, or sorry, the free body diagrams. Now we have to drive the equations from it. So in the earlier videos, as we were just talking about the single mass and the single spring, or the mass single mass with the spring and the damper, which means we were just talking about a one mass, but in this diagram we are having two masses, M1 and M2, as I have explained, M1 and M2 here. So we are going to have two net forces, and let's give them name Fnet1 and Fnet2. So let's say the force that will work on this one, will give this name Fnet1, and the force that will work on this one will give this name Fnet2. So to draw the to drive the equations from these free body diagrams, we have to start from a very simple equation. I'm just going to scroll this page a little bit upward, and we'll start from F equals to ma, as we know this equation number 1, and that is for the mass. And as we're using the spring constant, so we're going to use the Hooke's law, which is H equals to Kx. K is a spring constant and X is the displacement, which in this case is our displacement, that X is representing our displacement here and displacement here. So to let's write down the equations for Fnet1, and we know for Fnet1 we are having Fi, which is our input force, and which is going downward, and Fkt, the second reactive force, which is going upward. So which means the reactive force is in the opposite direction of the input original force, so we are going to minus Fkt from Fi. Now we got our fnet1, which let's give this equation number 2, but we don't know what is our fkt actually is. Fkt, which means k is a spring constant, so we are going to use the Hooke's law, and we are going to use the k times the displacement. Now for the m1, we are going to have a displacement between the spring is going to be displaced between this point and this point, which means we can actually simplify in this way, between this point and this point, so which means xt minus xs. So we are going to place this and this, both of these displacements here. So we are going to have xt minus xs, and let's give this equation number 3. Now let's jump on the second force, which is fnet2, and in this one we can see that fkt is working downward and fks is working upward, which means it's the same way as we've done in fnet1, and we're going to minus this fks from it. So now we got our fkt already here, but we don't have our fks, and for fks we are going to have same the spring constant, which means k times, now for k times the displacement, but in fnet2, which is relating to our fnet2, which is our m1, and in m1 we are having a displacement between this point and the ground, and we know the displacement at xs is represented by xs, and at the ground we are having a displacement 0. So I'm going to just place this xs here and minus ground, which will be replaced by 0. So we are going to have fks equals to k times xs minus 0. So our fks is equals to kxs. And let's give this equation number 4 and equation number 5. The only equations that we are going to use for to draw our block diagram is equation number 2, equation number 3, 4, and 5. I'm just gonna scroll this page down and let's start the block diagram now. So in order to draw the block diagram, first of all, I always say that always start from the integral part. The reason is because we are having a displacement, and displacement is the second derivative, which means when we'll have an acceleration integrated, we'll receive the velocity, and when we integrate the velocity, we'll get the displacement. So for one displacement, for one mass, we are having 2 blocks of integration, which means as in our diagram we are having 2 blocks of masses, m1 and m2, so we are going to have a total 4 blocks of integration. So we can start from, let's draw from here. We are having a 1 block of integration, that's having acceleration going into it, we having a velocity, and when we integrate the velocity we'll have a displacement, and let's give this name xt. And because we know xt is belong to m2, so this part is for m2, and we are having another mass as well, which is m1, so we have an acceleration, having a velocity out, we have another integral section, and we got this xs, and that is for m1. Now we got this acceleration here, we got our acceleration here, and because this belongs to m2, so we're just gonna use equation number 1, which is f equals to ma, and making this a as a subject, will make f over m, which actually we know is equals to f times 1 over m. So because we are using this A here, which is for M2, and for M2 we are going to multiply this 1 over M2, and that will be multiplied by F, which is actually our fnet1 from here, and we are just going to write down this name fnet1, and we know fnet1 is actually sum of two forces, which is Fi minus Fkt. So I'm just gonna insert into positive Fi and minus Fkt. Now let's jump, because we finished this equation, so now let's jump on the equation number 3 and let's figure it out. What is Fk2? As we can see from here that Fkt is actually K, which is a spring constant, times the displacement xt minus xs, and we can see that xt is here and xs is here. All we have to do is to just send them into the summation block with their corresponding signs. So we call the summation block here, in which xs and xt is going, and as we know xs is negative and xt is positive, and we're just gonna multiply this with the spring constant k and send the feedback back into the fkt as a negative for this one. So we are done with our this equation as well. Now let's jump on fnet2, which is our equation number 4, and let's prove this one. As we know, to prove this one, we are having fkt minus fks. So definitely for fnet2 we are having the summation of two forces as well. So I'm just gonna put this one here, and let's send these we having minus fks, and this fkt will go exactly the same way here, which is positive. Now let's we figure it out that this is equals to fnet2. Now where this fnet2 is going, now as we know that here is acceleration related to xs, and which is for m1. So for m1 we're going to use exactly the same formula, because we're having an acceleration here, and acceleration is came out of f equals to ma. Keeping a as a subject, we're having f over m, and which means f times 1 over m, but just replace this m with m2 and f with fnet2. So we are having this block here, which is 1 over m1. Sorry, this is not m2, this is m1. Let's place this m1. I'm just gonna make this block a bit bigger so it's much easier to understand. We go our 1 over m1, and this f2 is going inside, and all we're left over with proving this this equation, which is fks equals to what. So we are done with our equation number 3 as well. Let's put a tick on it, and now we are jumped on the last equation, equation number 5. So for equation number 5, as we can see here, is fks equals to k times displacement which is xs, and xs is here, and we got fks here, which means all we have to do is to take this displacement, send it into a block, which means we are multiplying the k, which is our, let's give this name, this is a k, and this k is multiplying and going back as a negative feedback into the summation block, and that's all. We are done. So as we can see, it was a little bit more lengthy than the last video that I uploaded, and this is a very simple method to solve these block diagrams. These block diagrams by looking at these mechanical or physical system of models, then turning them into a free body diagram, and then you convert these diagrams into the equations, and then looking at those equations you can just simply draw these block diagrams, and that's all. We are done with this question. Thank you very much for watching this video, and please don't forget to like, subscribe, comment and share this video, and please hit the bell icon so whenever I will upload the new video you will get the notification. And in the next videos I am going to bring a very interesting questions relating to electrical as well, and drawing their free body diagram, then drawing their block diagram, then reducing them, and we'll also cover the transfer functions for the first order, second order, third order, and the Routh-Hurwitz method as well. So please stay tuned and just subscribe my channel. I need your support, and we'll see you in the next video. Thank you very much.